This final mutation video is all about nonsense mutations and frameshift mutations. So just to recap, a silent mutation occurs when the mutation at the DNA level results in the same amino acid being incorporated during translation. So it does not harm the cell. A missense mutation is a mistake. The mutation, which happens at the DNA level, is going to result in a different and incorrect amino acid being incorporated into the growing polypeptide chain. Now, depending on which incorrect amino acid gets incorporated, sometimes the protein just misfolds a little bit, but it's still generally the right shape, so it can do its job and the cell is okay. Maybe the protein can still fold, but it's not quite as efficient. So the cell may have some issues, but it may not be fatal. But if a completely different amino acid, like it has total opposite charges, is incorporated, it could cause the protein to completely misfold, in which case it can't do its job and the cell, and therefore, depending on the organism, may die. Okay, so we're starting with our same information that was on videos 1 and 2, but now we are going to cause a different mutation here. So let's illustrate it. So I'm going to draw a line through this second nucleotide. Okay, and instead of guanine, good old dipole got confused and added a thymine instead. Okay, so now let's look at the trickle down effects that this is going to have. So instead of having the codon UCG, we're going to have the codon UAG. So now look at your codon wheel, and instead of serine, what are we going to have? We're going to have nothing, because UAG is a stop codon. There is no amino acid, okay, for a stop codon. So that means in this example, translation never actually occurs, because the first thing it's going to try and do is release the ribosome and release the messenger RNA. Because remember, that's what a stop codon does. A release factor binds to the ribosome and causes everything to disassemble. So in this case, no protein is even started, okay? Now, so that's what a nonsense is. I remember this one by saying a nonsense is not tolerated. You get a premature stop codon, which means it's a premature termination of translation. Translation stops too soon, okay? It doesn't make the entire protein. In this example, it's not making any protein. But what you do need to know is, remember, most proteins are a minimum of 500 amino acids. So, and again, none of these in this example, I don't think there's any other way I can make a stop codon. But if we just pretend, hold on, I'm trying to get my pen back up. Maybe somewhere down the line, I'm just going to use methionine here just as an example. If the stop codon was introduced here instead, the protein, the ribosome still would have added serine, histidine, glycine, but then it would be terminated. Okay, so with a nonsense mutation, it can occur anywhere in the protein sequence, but no matter what, it's introducing a premature stop codon. So it's terminating translation prematurely. And no matter where it's at, that's normally no good. Okay, so this will normally be fatal to the cell. It's much less tolerated, especially if it happens at the beginning of the protein or at the beginning of translation, so that most of the protein isn't even made. Okay. All right, so now I'm going to go ahead and erase this little X here. For frameshift, remember in the first mutations video, I mentioned that this is going to be what's called an indel. So either an insertion or a deletion is going to result in a frameshift mutation. And so that's where, for whatever reason, DNA polymerase got confused and either added an extra nucleotide or he skipped one altogether. So I'm going to go ahead and show you an insertion. So maybe after the first 3 nucleotides, he's going to add an extra cytosine. Okay, so that's the mutation. I've illustrated it by just drawing it in. And so what that means now is when RNA polymerase comes along to make a strand of RNA polymerase doesn't know that's a mistake. It completely trusts the template DNA, okay? So it's going to add a guanine in there. So now let's indicate our reading frame by underlining. I'm going to underline it in green. So UCG is still good. It has not been affected. But now our second codon is going to be GCA. Our third codon is UGG. And then the fourth codon is GAU, right? And this would continue on down the entire thing. So now when we think about translation, where we're making our protein, okay, so UCG is still going to give us serine, so that's good. But now our second codon is GCA. GCA gives us alanine, okay, so that's different, so And then next up is going to be UGG. UGG gives us tryptophan. And then GAU is going to give us aspartate. Okay, so as you can see, everything is wrong. Okay, we are making some completely random protein that the cell doesn't need, which means we're also not making the correct protein that the cell does need. And eventually what's going to happen is we're going to make a premature stop codon. Okay, so frameshift is really bad for the organism because it's making something random. Who knows what's going to be the consequence of having some totally random, protein in our cell, but it's also not making what it needs. So that was an insertion. The exact same thing is going to happen with a deletion. Okay, so let me do this real quick. But again, by having one less nucleotide, it's going to throw off our reading frame. So I'm going to go ahead and just mess with nucleotide number 2. So pretend after laying that first adenine, DNA polymerase just for some reason got confused and didn't incorporate that guanine at all. Okay, so that means now in my RNA, I don't have that cytosine. Okay, so now let me go ahead and underline my codons. So now my first codon is UGC. My second is AUG, and then GGA, and so on and so forth. So now let's look at what happens after translation. What does UGC give us? It gives us cysteine. Okay, AUG gives us methionine. I know that one by heart. And then GGA gives us glycine. Hey, that's good. And then UG, we don't know. We don't have a third codon there. So, but notice again, we're making the entirely wrong thing. Okay, so again, that is going to be pretty bad for the cell. All right, y'all, that's the end of the mutation talk.